Hello, everyone, and welcome back to the lecture series on natural and synthetic macromolecules. In nature, we find many substances with very high molecular masses that contribute significantly to the structure of living organisms and tissues. Some examples include starch and cellulose, which are abundant in plants, and proteins, found in both plants and animals. In 1827, Swedish chemist Jöns Jacob Berzelius introduced the term polymer to describe molecular substances of high molecular mass formed by the joining together of monomers, that is, molecules with low molecular mass. This process is referred to as polymerization, and as an example, you can see here the reaction of ethene monomers forming polyethene. For a long time, humans have processed naturally occurring polymers, such as wool, leather, silk, and natural rubber, into usable materials. Over the last century, however, chemists have learned to synthesize polymers by polymerizing compounds through controlled chemical reactions. Many of these synthetic polymers have a backbone of carbon-carbon bonds because carbon atoms have an exceptional ability to form strong, stable bonds with one another. Plastics are specific examples and can be molded into various shapes, usually by the application of heat and pressure. Furthermore, thermoplastic materials can be reshaped. For example, plastic milk containers are made from a polymer known as polyethylene, which has a high molecular mass. These containers can be melted down, and the polymer can be recycled for other uses. We also have access to thermosetting plastics, which are shaped through irreversible chemical processes and thus cannot be readily reshaped. In this lecture, our objectives are to recognize the relationship between a monomer and a polymer, understand the three stages of the addition polymerization process, and make the link between the macroscopic properties of polymers and molecular level properties, such as crystallinity and cross-linking. Polyethylene is a solid substance used to make thousands of plastic products, such as plastic bags, food containers, and laboratory equipment. To produce polyethylene, we must create a reactive center that can sequentially add to the double bond in each ethene molecule, extending the polymer chain and regenerating the reactive center for follow-up additions. Such reactions are classified as chain growth or addition polymerizations, and polyethylene is an addition polymer. In ethene polymerization, the reactive center that initiates polymerization is frequently a free radical. You might recall radicals and radical substitution reactions from the lecture describing types of organic reactions. In the case of ethene polymerization, radicals are commonly derived from a radical initiator, such as lauryl peroxide. These molecules contain a very weak oxygen-oxygen bond and readily dissociate to form two radicals upon heating or irradiation with light. Once formed, the benzoyl radical can add to the double bond of ethene to form a new carbon-centered radical. This step is called the initiation step. Note the use of fishhook arrows in this equation. They differ from traditional curly arrows, which represent the movement of two electrons. Fishhook arrows represent the movement of a single electron rather than an electron pair. The relative stabilities of alkyl radicals are as follows. Radicals centered on a tertiary carbon are more stable than radicals centered on secondary carbons, and the least stable are primary radicals. The next stage of the reaction is known as propagation. In this stage, the chain is extended by the consecutive addition of more ethene units through carbon-carbon bond-forming reactions. This process can be repeated multiple times, prolonging the hydrocarbon chain by 2 carbon subunits after each addition step. Propagation continues until 2 radical polymer chains meet and react, forming a completed polymer through a final carbon-carbon bond formation that terminates the radicals. This is known as the termination step. In the structure presented here, N and M are normally large integers, which may or may not have the same value. The reactive center in a chain growth polymerization does not have to be a radical. Depending on the monomer used, it may be an anion, a cation, or a transition metal complex. For instance, the most common process for polyethylene production is called Ziegler-Natta polymerization, named after the two scientists who developed the reaction in the 1950s. This process typically involves zirconium, titanium, or aluminum complexes as catalysts and is used in the formation of high-density polyethylene, also called hard plastic. An example of a Ziegler-Natta polymerization is shown here. These processes are quite complex and are beyond the scope of this course. Ziegler-Natta polymerization produces simple straight chains. In contrast, radical polymerization of polyethylene gives a polymer with occasional long branches, making it harder to pack the molecules together. The result is low-density polyethylene, which is used in stretchy plastic wrap. We can write the overall equation for the polymerization of ethene as follows. Here, N represents the large number of monomer molecules that react to form one large polymer molecule. The values of N can range from hundreds to many thousands. Within the polymer, a repeating unit appears along the entire chain. In this equation, the repeating unit for polyethylene is shown in brackets. Polyethylene is a very important commercial material. More than 10 billion kilograms of polyethylene are produced globally each year. This is a huge amount. It is equivalent to the weight of about 1.4 billion people and is roughly 100 times the weight of the Eiffel Tower. However, although polyethylene has a simple composition, manufacturing this polymer is not an easy task. Only after many years of research were the right conditions identified for its production. Today, many different forms of polyethylene, varying widely in physical properties, are known. Polymers with other chemical compositions provide an even greater variety of physical and chemical properties. In this table, you can see several other common polymers obtained by addition polymerization. The names of polymers are simply derived from the monomers used. For example, poly, vinyl chloride, is made from vinyl chloride. Poly-methyl methacrylate is made from methyl methacrylate, and polystyrene is made from styrene. In 1938, a scientist at DuPont named Roy Plunkett made a rather curious observation. A tank of gaseous tetrafluoroethene that was supposed to be full seemed to contain no gas. Rather than discard the tank, Plunkett decided to cut it open. He found that the inside of the tank was coated with a waxy white substance that was remarkably unreactive, even toward the most corrosive reagents. That compound was formed by the addition polymerization of tetrafluoroethene. As it turned out, the properties of this material, called Teflon, were ideal for an immediate and important application, the development of the first atomic bomb. Uranium hexafluoride, which was used to separate radioactive uranium-235 by gaseous diffusion, is an extremely corrosive material. Teflon was applied as a gasket material in the separation of uranium-235. Today, Teflon is used in a variety of applications, from nonstick cookware to spacesuits. Plunkett's desire to learn more about something that didn't seem right is a wonderful example of how natural scientific curiosity can lead to remarkable discoveries. To sum it up, in this lecture, you were introduced to synthetic polymers produced by addition polymerization. You now know that polymers are molecules of high molecular mass formed by joining together large numbers of smaller molecules, called monomers. In a chain growth or addition polymerization reaction, the molecules form new linkages by opening double bonds. We studied polyethylene and briefly went through the 3 stages of polymerization, commonly called initiation, propagation, and termination. In the following lecture, we will examine the physical properties of some addition polymers and see how they relate to the structure of the polymer. Thank you for your attention.